You've seen a spring a million times. It's just a simple coil of metal, right? It pushes, it pulls, seems pretty basic. But what if I told you that inside this everyday object, there's a whole world of advanced engineering, a constant battle between materials, shapes, and hidden stresses? Today, we're going to uncover the unseen engineering of springs. So the big question is, how do you even begin to reinvent something so fundamental? I mean, it's a spring. But the answer isn't some single magic breakthrough. The innovation is happening everywhere, at every level, right down to the atoms the spring is made of, to its exact, precise shape, and even how it's put together. It really all boils down to pushing the limits in three key areas. First, the materials we use. Second, the geometry we design. And third, the manufacturing processes that actually bring it all to life. So let's break each one down. All right, first up, the material makeover. This is a big one. The classic steel spring we all know is getting a massive, massive upgrade. And we're not just talking about a slightly stronger kind of steel. No, we are talking about completely reimagining what a spring can even be made of. For the longest time, steel was king. It was strong, it was reliable, but man, was it heavy. Today, the game has totally changed. We're now using these advanced composites that are, get this, not only stronger than steel, but also way, way lighter. And the best part? You can customize them for incredibly specific jobs, whether it's for a high-performance race car or state-of-the-art prosthetic. And this ability to customize leads to some just incredible advantages. I mean, you get a superior strength-to-weight ratio. That's huge for making cars more fuel efficient. These materials also offer better damping, which basically means more stability and a smoother ride. You can literally design a spring to respond in a very specific way, and then you can add things like fiber reinforcement to boost its performance even more. And then you get into the really futuristic stuff, like auxetic materials. Okay, try to wrap your head around this. You take a normal rubber band and stretch it, and it gets thinner, right? Simple. Well, as Svikhanen's research from 2024 explores, if you stretch an auxetic material, it actually gets thicker. It's completely counterintuitive, and this bizarre property opens the door for some truly unique and amazing spring designs. But of course, it's not all that easy. These newfangled materials come with their own unique set of problems. Research from Agarwal and his colleagues points out a big one for composites: delamination. The best way to think of it is like a sheet of plywood starting to peel apart. The layers separate, and suddenly it's not so strong anymore. So the real genius isn't just in inventing new materials, it's in mastering their weaknesses too. So you've got your fancy new material. That's great. But that is only half the battle. The other half, which is just as important, is its shape. Because in the world of springs, geometry is everything. Okay, here's a basic rule in engineering. Anytime you have a sharp corner or an abrupt change in shape, it acts like a magnet for stress. All the force gets concentrated right there. Now, in a spring that's designed to flex and bend thousands, maybe millions of times, those stress concentrations are exactly where failures begin. It's a recipe for disaster. Just look at this. On the left, you see that sharp corner? That's the weak spot. All of the stress is piling up right there. But now look to the right. By simply rounding that corner, as Mikulchik and his team have shown, you spread that stress out evenly. It's a tiny, tiny change, but it's the difference between a spring that breaks after 1,000,000 cycles and one that can last for 10 million. It's incredible. And there's another huge geometric puzzle called springback. You know when you bend a paper clip and when you let go it sort of bounces back a little? That's springback. Now imagine that on an industrial scale. According to research from Nowinski in 2024, if you don't perfectly predict and account for how much that material is going to spring back, your final product won't have the exact dimensions you need. The whole design could be useless. And that brings us to our third and final piece of the puzzle, the art of perfection. Because look, you can have the absolute perfect material and the perfect geometric design, but if you don't manufacture and finish it just right, all of that potential goes right out the window. Think about it. When you take a piece of steel and you force it into a coil shape without heating it up, you're not just changing its shape. You are packing it full of invisible internal tension. These are hidden forces locked deep inside the metal, and they're basically fighting against the very job the spring is supposed to do. So how do you get rid of that hidden tension? Well, you send the spring to a spa. Kind of. It's a process called stress relieving. Based on work by folks like Greenfield, you take the finished spring and you heat it up very carefully. It's almost like you're telling the atoms inside to just take a deep breath, relax, and settle down into a much more stable state. And here is the absolute magic of it. Research from Fahad and his team confirmed that this heat treatment gets rid of all those nasty internal stresses without changing the spring's precise shape one bit. So you get all the stability and strength benefits without sacrificing the perfect geometry you worked so hard to design. It's the best of both worlds. So let's just tie this all together for a second. As you can see, it's not a one-size-fits-all solution. For your classic helical or coil spring, the big challenge is predicting that spring back to get the dimensions just right. For a modern leaf spring made of composites, you're fighting against delamination and trying to save weight. And for a really complex machined spring, the number one enemy is stress, building up in those corners. Each type is its own unique engineering puzzle. Okay, so we've dived deep into the materials, the geometry, and the process. Now let's zoom back out and talk about the real world, because the future that this technology is building, well, it's incredibly flexible. You might be thinking, okay, that's a lot of work for a humble little spring. So why does it matter? Why go through all this trouble? Because here's the thing. Better springs don't just mean better springs. They mean better, well, better everything. Think about it. Those lighter composite springs, that means cars that use less fuel. Better designed springs give you a smoother ride and safer handling. For huge industrial machines, it means they last longer and break down less. And looking forward, things get even wilder. Researchers like Thierry Onay and Roux are exploring how to use advanced springs to harvest energy just from vibrations. Others, like Mougerets, are studying how they can help manage heat. It's amazing. So the next time you see a spring, whether it's in a clicking pen or in your car's suspension, maybe you'll see it a little differently. Remember that invisible world of engineering hiding inside, that incredible dance between material science, precise geometry, and the art of perfection. And it really does make you wonder, doesn't it? What other simple, everyday objects are hiding a whole world of complex engineering?